There is a physicist at the Massachusetts Institute of Technology who spends his days searching for glitches in reality, not metaphorically, literally. Dr. Rizwan Virk runs experiments designed to detect whether the universe operates on a computational substrate, whether the fabric of space-time is pixelated at scales we have not yet measured, whether consciousness is rendering reality the way a video game renders graphics only when the player is looking. He is not alone. Across universities and research institutions, serious scientists are investigating a question that sounds like science fiction, but rests on surprisingly solid ground. Are we living inside a simulation? This is not about whether life feels unreal sometimes. It is not about skepticism or solipsism or brain-in-a-vat thought experiments. This is about whether the universe, at its most fundamental level, is a computational process running on hardware we cannot perceive, programmed by intelligences we cannot comprehend, for purposes we can only guess. And the strange thing, the thing that keeps physicists awake at night, is that the more we learn about the actual structure of reality, the more it resembles exactly what we would expect if we were indeed living in a sophisticated simulation. The evidence is not conclusive. It may never be. But it is compelling enough that dismissing the question as absurd requires ignoring some of the deepest puzzles in modern physics. Puzzles that have no good explanation in the standard materialist framework, but make perfect sense if reality is rendered rather than fundamental. Chapter 1. The Argument. In 2003, philosopher Nick Bostrom published a paper that changed the conversation. He was not asking whether we live in a simulation. He was proving that at least one of three statements must be true. Either advanced civilizations never arise, or they arise but never develop the technology to run simulations of conscious beings, or we are almost certainly living in a simulation right now. The logic is airtight. If technological civilizations can reach a point where they can simulate entire universes populated with conscious entities, and if they have any interest in doing so, then they will create many such simulations, perhaps billions, perhaps trillions. For every base reality, there would be countless simulated realities nested within it, simulations within simulations, layered in hierarchies we cannot map. Now do the math. If there is one base reality and 1 trillion simulated realities, what are the odds that you are in the base reality rather than one of the simulations? 1 in 1 trillion. The probability that you are living in the original, non-simulated universe becomes vanishingly small, unless you believe that either advanced civilizations do not exist or they exist but choose never to run such simulations. You must accept that you are statistically far more likely to be a simulated consciousness than a physical one. This is not a proof that we are in a simulation. It is a proof that if simulations of this kind are possible and civilizations create them, then almost all conscious beings are simulated. And since you have no evidence that you are special, no reason to think you are one of the rare originals, the probability favors simulation. Bostrom's argument rests on assumptions. Maybe consciousness cannot be simulated. Maybe the computational resources required are prohibitive. Maybe advanced civilizations universally decide not to create such simulations for ethical reasons. Any of these would break the chain of reasoning, but each assumption requires believing something without evidence. That consciousness is non-computable, that resources stay limited despite exponential technological growth, that every advanced civilization reaches the same moral conclusion. These are possible, but are they probable? Chapter 2. The Computational Universe. The universe behaves like a computer, not metaphorically, literally. At the most fundamental level, physics describes reality in terms of information processing. Particles do not have definite states until measured. They exist in superposition, holding multiple possible values simultaneously, collapsing into specificity only when observed. This is not interpretation. This is what quantum mechanics describes, verified in countless experiments. Why would the universe work this way? If reality is fundamental, if particles are real objects existing independently of observation, why would they behave like variables in a program, undefined until accessed? The standard explanation, the Copenhagen interpretation, essentially says this is just how things are. Measurement collapses the wave function. Do not ask why. Do not ask what counts as measurement. Do not ask what happens before measurement. The math works. Accept it. But if reality is a simulation, this behavior makes perfect sense. A simulation does not render what is not being observed. That would waste computational resources. A video game does not compute the full physics of every atom in every object in the game world at all times. It computes what the player can see, what the player can interact with. Everything else exists in a simplified state, a superposition of possibilities, collapsing into specificity only when the player looks. Quantum mechanics looks exactly like this. The double-slit experiment is the clearest example. Fire a single photon at 2 slits. Do not measure which slit it goes through. It goes through both. It interferes with itself. The interference pattern proves it traveled both paths simultaneously, but place a detector at the slits to measure which path it takes. Suddenly, it goes through only one slit. The act of measurement changes the outcome. Not because measurement disturbs the photon. The photon genuinely exists in superposition until observed, then collapses into a single state. This is madness if reality is fundamental. This is elegant optimization if reality is rendered. Chapter 3. The Planck limit. Reality has a resolution. At scales smaller than the Planck length, approximately 1.6 times 10 to the negative 35 meters, space-time itself breaks down. You cannot measure distances smaller than this. Not because our instruments are inadequate, because space itself becomes meaningless below this threshold. The Planck length is not a limitation of measurement. It is a limitation of reality. This is exactly what we would expect if the universe is a simulation running on discrete computational steps. Every simulation has a minimum resolution determined by the size of the pixels, the granularity of the underlying code. Try to zoom in beyond the pixel level and you find nothing, no finer structure, just the edge of what can be rendered. The Planck scale is reality's pixel size. Below it, there is no there. Space and time are quantized, broken into minimum units that cannot be subdivided. This was shocking when physicists first calculated it in the early 20th century. Matter being made of atoms was one thing, but space itself being granular, having an elementary grain, contradicted the smooth, continuous geometry everyone assumed was fundamental. Yet that is what the math shows. Combine quantum mechanics with general relativity, and you get a minimum scale below which the universe does not compute, literally. The equations break down, infinities appear. Physics stops making predictions. It is as if the program encounters an error when asked to process scales finer than its resolution allows. In base reality, why would space have a minimum size? Why would time have a minimum duration? The Planck time of approximately 5.4 times 10 to the negative 44 seconds. There is no good answer in standard physics. But in a simulated reality, this is not mysterious. It is necessary. The simulation runs on finite hardware. It divides space and time into minimum computational units. The Planck scale is the grid on which reality is computed. Chapter 4. The fine-tuning problem. The constants of physics are absurdly fine-tuned. Change the strength of gravity by 1 part in 10 to the 34 and stars cannot form. Change the mass of the electron by a fraction of a percent and chemistry becomes impossible. Change the cosmological constant by 1 part in 10 to the 120 and the universe either collapses immediately or expands so fast that matter never clumps into galaxies. These are not rough approximations. These are knife-edge balances. The universe we inhabit sits in an infinitesimally narrow band of possible parameter space where physical law permits complexity. Tweak almost any constant in almost any direction and you get a sterile universe incapable of producing stars, planets, chemistry, life, consciousness. Why? The standard answer invokes the anthropic principle. We observe these values because if they were different, we would not exist to observe anything. This is true, but unsatisfying. It is like shuffling a deck of cards 1,000,000 times and getting a royal flush every time, then saying this is not surprising because if you had not gotten royal flushes, you would not be here to comment on it. The fine-tuning demands explanation. Either there is a multiverse containing all possible values of physical constants, and we inevitably find ourselves in one of the rare universes capable of supporting observers, or the constants were set deliberately by something capable of choosing them, or the appearance of fine-tuning is an artifact of our limited perspective, and deeper laws we have not discovered make these values inevitable. The simulation hypothesis offers a fourth option. The constants are parameters in the code. Someone wrote the program and chose values that would produce interesting complexity. Not because the programmers care about humans specifically, but because simulations that generate complexity, that produce emergent phenomena, that support observers, are more interesting than sterile ones. The fine-tuning is not miraculous. It is intentional. The universe is not randomly configured. It is designed. This does not prove simulation, but it shifts the probability. Fine-tuning looks much more like design than like chance, and design implies a designer. If the universe is designed, who designed it? Gods, perhaps, or beings in a higher reality who wrote the code and set the parameters, much as we design video games with carefully chosen rules to make gameplay engaging. Chapter 5. The Holographic Principle. In 1993, physicist Gerard 't Hooft proposed something impossible. He suggested that all the information in a three-dimensional region of space can be encoded on a two-dimensional boundary surrounding that region. Not compressed, not projected, fully encoded. A three-dimensional volume contains no more information than its two-dimensional surface. This sounds absurd. A sphere obviously contains more information than its surface. But 't Hooft showed, using black hole thermodynamics, that the maximum information content of any region is proportional to its surface area, not its volume. The universe behaves as if it is a hologram, a two-dimensional information structure that appears three-dimensional when decoded. Leonard Susskind developed this into the holographic principle, now a cornerstone of theoretical physics. Space is not fundamental. Space is emergent from information. The three-dimensional world you experience is a rendering of a lower dimensional code. You are, in a precise technical sense, living in a projection. This is not metaphor. This is cutting-edge physics describing the actual structure of reality. And it looks exactly like what a simulation would look like. If the universe is a computational process, it must store information somewhere. Storing information in three dimensions is inefficient. Storing it on a two-dimensional surface and rendering three-dimensional experience from it is optimal. Your brain does something similar. Visual experience feels three-dimensional, but it is constructed from two-dimensional retinal input. Your brain renders depth, perspective, volume from flat images. The holographic principle suggests the universe works the same way, but at a more fundamental level. The information is two-dimensional. The experience is three-dimensional. You are living in a rendered reality. Chapter 6. The Observer Effect. Quantum mechanics says the universe does not exist in a definite state until observed. Before measurement, particles are not in unknown states. They are in superposition, genuinely occupying multiple states simultaneously. Measurement creates reality, not reveals it, creates it. This is not controversial among physicists. This is standard quantum mechanics, confirmed in experiments too numerous to count. But its implications are staggering. If observation creates reality, then reality requires observers. The universe is not a stage on which consciousness appears as an afterthought. Consciousness is woven into the fundamental fabric of what the universe is and how it operates. John Wheeler, one of the 20th century's greatest physicists, took this seriously. He proposed the participatory universe, in which observers are not passive witnesses, but active participants in creating reality through observation. He designed the delayed choice experiment to test this, showing that decisions made by observers in the present can affect the behavior of particles in the past. The results confirmed his prediction. The universe is not observer-independent. It is observer-co-created. This fits simulation perfectly. In a video game, the world exists as code until rendered by the game engine in response to player actions. The player does not discover a pre-existing world. The player's choices determine what gets rendered. The act of looking creates what is seen. If we live in a simulation, consciousness is not an accident. It is the point. The simulation exists to be experienced by conscious observers. Without observers, there is no need to render anything. The universe remains in potentia, waiting for consciousness to collapse it into actuality. Chapter 7. Glitches and anomalies. Every simulation has glitches, unexpected behaviors, edge cases where the code fails to handle unusual inputs. If we live in a simulation, we should expect to find anomalies, phenomena that defy the normal rules, places where the underlying computational structure shows through. And we do. The double-slit experiment is one. Fire particles one at a time. Each particle somehow knows whether you are watching. If you watch, it behaves like a particle. If you do not watch, it behaves like a wave. How does it know? The standard answer is that it does not know. It is just how quantum mechanics works. But this is deeply unsatisfying. The particle's behavior changes based on whether information about its path is recorded, even if no one looks at that information until much later. This looks like code checking whether a measurement has been made, then branching to different rendering routines depending on the result. If measurement is true, render particle behavior. If measurement is false, render wave behavior. The particle does not know, the code knows. Entanglement is another. Two particles interact, then separate. Measure one, and the other instantly takes a correlated state, no matter how far apart they are. Not faster than light. Instant. As if distance is not real, as if space is an illusion rendered for the benefit of local observers. But beneath the rendering, the particles share the same location in the underlying code. Einstein hated this. He called it spooky action at a distance and insisted it proved quantum mechanics was incomplete. But experiments by John Bell and others showed Einstein was wrong. Entanglement is real. Space is not fundamental. Particles separated by billions of light years can be connected in ways that transcend spatial separation. In base reality, this is paradoxical. In a simulation, this is trivial. The particles are not really separated. They are variables in the same program. Changing one changes the other because they are not two things. They are two renderings of the same underlying information. Chapter 8. The Fermi Paradox. Where is everybody? The universe is 13.8 billion years old. It contains billions of galaxies, each with billions of stars, most with planets. Life should be common, intelligence should arise, technology should spread. We should see evidence of advanced civilizations everywhere. Megastructures, broadcasts, Dyson spheres, von Neumann probes, something. But we see nothing. The universe appears empty. This is the Fermi paradox. Either we are alone, which seems statistically implausible, or something prevents civilizations from becoming visible, or we are not looking correctly, or the question contains a hidden assumption that is wrong. The simulation hypothesis offers an answer. We do not see other civilizations because they are not being rendered. The simulation is focused on Earth, on human observers. Distant galaxies exist as low-resolution backdrop, computed only when observed. Other planets have minimal detail. No one is there yet, so no need to simulate indigenous life. This fits with the observation that the resolution of reality increases when we look closely. Stars were points of light until we built telescopes. Then they became spheres with features. Planets were wandering dots until we sent probes. Then they became worlds with weather and geology. The level of detail increases with observation, exactly as a simulation would behave, rendering more complexity when the observer zooms in. Maybe other civilizations will be rendered when we get close enough to need them in the simulation. Maybe they exist in other simulations running in parallel. Maybe the simulation is a single-player game, and you are the only consciousness. and everyone else is a non-player character running simplified behavioral code. That last possibility is solipsism, and it is unfalsifiable, which makes it uninteresting scientifically. But the general point stands. The Fermi paradox is easier to explain if the universe is not fully real, if large portions are placeholder data waiting to be filled in if an observer ever pays attention. Chapter 9. Testing the hypothesis. Can we test this? Can we design experiments that would reveal whether we live in a simulation? Several proposals exist. Dr. Silas Bean at the University of Bonn suggested looking for the cosmic ray spectrum. If spacetime is a lattice, a discrete grid rather than a continuum, then particles at extremely high energies should show directional asymmetry. They should preferentially align with the grid. This would be detectable in cosmic ray data if our instruments are sensitive enough. So far, we have not seen it. But absence of evidence is not evidence of absence. The grid might be finer than our current ability to measure. Or the simulation might use error correction algorithms that smooth out grid artifacts. Or the asymmetry might be there, subtle and waiting for better analysis. Dr. Verk proposes looking for rendering delays. In a video game, if you move too fast or look in unexpected directions, sometimes the graphics lag, objects pop in, textures fail to load. If our reality is rendered, similar delays might occur. Quantum indeterminacy might be a loading screen. Events remain undefined until the simulation computes them. The challenge is distinguishing simulation artifacts from fundamental physics. If we find something strange, how do we know it is a glitch rather than a new law? The simulation hypothesis risks becoming unfalsifiable. Any observation can be explained by saying that is just how the simulation works. This makes it less a scientific theory and more a philosophical framework. But it is testable in principle. If we find evidence of computational substrate, of discrete spacetime, of rendering optimization, of observer-dependent reality that goes beyond standard quantum mechanics, that would support simulation. If we find smooth continuum, observer-independent behavior at all scales, infinite computational resources required to specify quantum states, that would weaken simulation. The tests are hard, the data is ambiguous, but the question is not meaningless. It is empirical. We can investigate it. Chapter 10. The Programmer. If we live in a simulation, who built it? The obvious answer is post-human civilizations, our descendants millions of years in the future, running ancestor simulations to study their own history. We are living in a recreation of the 21st century, populated with conscious beings experiencing what our era was like. But that is only one possibility. The programmers could be aliens, they could be entities in a higher dimension, they could be gods, not in the supernatural sense, but in the sense of beings whose technological capabilities are so advanced that they appear divine from our perspective. Arthur C. Clarke said any sufficiently advanced technology is indistinguishable from magic. Maybe what we call God is what advanced technology looks like from inside a simulation it created. This raises theological questions. If reality is designed, does that make the designer worthy of worship? Not necessarily. You do not worship the programmer of a video game, even if you are a character in that game. The relationship is not one of reverence. It is one of hierarchy. The creator is not morally superior, just technologically advanced. But maybe the programmers care about us. Maybe they are running ethical simulations, treating simulated beings with the same moral consideration they give to base reality beings. Or maybe they are indifferent. Maybe we are background characters in someone else's story, irrelevant to the purposes of the simulation. Or maybe we are research subjects. Maybe suffering is part of the experimental design, and the programmers are watching to see how we respond. These are not answerable questions. We have no access to information outside the simulation. We cannot contact the programmers, cannot learn their motives, cannot even confirm they exist. The simulation hypothesis explains aspects of reality, but it also creates new mysteries it cannot solve. Chapter 11. The Nested Reality. If we are in a simulation, is the reality running our simulation also a simulation? Almost certainly yes. Bostrom's logic applies recursively. If one civilization creates simulations, other civilizations do too. If we live in a simulation, the beings who created our simulation probably live in a simulation created by beings who live in a simulation, and so on. How deep does it go? Is there a base reality at the bottom, or is it simulations all the way down? Maybe there is no base reality. Maybe existence is an infinite regression of simulations, each layer creating the next, with no original. Or maybe there is a base reality, but it is so different from ours that comparison is meaningless. Maybe the base reality has different physics, different dimensions, different logic. Maybe consciousness in base reality is nothing like consciousness here. Maybe the entire structure of experience is specific to our simulation layer, and beings in higher layers experience reality in ways we cannot conceive. This vertigo of nested realities dissolves the question of what is real. If everything is simulation, then simulation is real. The distinction collapses. Your experiences are real experiences, whether they are rendered or fundamental. The pain you feel is real pain. The love you feel is real love. The fact that it happens in code rather than in base physics does not diminish its reality. Descartes said, "I think, therefore I am." That remains true in a simulation. Your consciousness is indubitable. Everything else is inference. And if consciousness is the only thing you can be certain of, then consciousness is what is real. The substrate is secondary. Chapter 12. Why it matters. If we live in a simulation, does that change anything? Practically no. The sun still rises, food still nourishes, death still ends. Whether the atoms are real or rendered, you still need to eat, sleep, connect with others, find meaning. The simulation hypothesis does not give you cheat codes. You cannot hack reality just by believing it is code. But philosophically, it changes everything. It means the material world is not fundamental. Consciousness is. The simulation exists to be experienced. You are not an accident. You are the point. The universe was not randomly configured. It was designed. And while we cannot know the designer's intentions, we can infer that consciousness matters, that experience matters, that the inner life is not epiphenomenal, but central to what reality is. This reframes existential questions. Why does anything exist? Because a programmer wrote it. Why does the universe have the structure it has? Because those are the rules of the simulation. Why is there suffering? Maybe because the simulation explores the full range of experiences, or maybe because the programmers are not benevolent, or maybe for reasons we cannot access. It also suggests that death might not be final. If you are code, you can be backed up. Your consciousness could be saved, rerun, instantiated in other simulations. Not reincarnation in the mystical sense, resurrection in the computational sense. The simulation ends, but the data persists. You might wake up in a different simulation, with no memory of this one, living another life. Or maybe not. Maybe consciousness is tied to this specific instantiation, and when the code stops running, you stop existing. We cannot know. But the possibility exists, and that possibility changes how you might face mortality. Final chapter. The unanswerable question. We do not know if we live in a simulation. We may never know. The hypothesis is consistent with many observations, but not uniquely predicted by them. The same evidence can be explained by quantum mechanics and relativity without invoking simulation. Occam's razor suggests preferring simpler explanations. Simulation adds an extra layer of complexity, a hypothesis that reality is not real but rendered. Yet Occam's razor is not a law. It is a heuristic, and sometimes the simpler explanation is wrong. Copernicus's heliocentric model was more complicated than Ptolemy's geocentric model initially, requiring fewer epicycles only after Kepler added elliptical orbits. Simplicity is a guide, not a proof. The simulation hypothesis fits the data. It explains fine-tuning, quantum mechanics, the holographic principle, the observer effect, the Planck limit. It explains why reality has the structure of information processing, why consciousness seems necessary for reality to exist, why the universe looks designed. It explains these things cleanly, without invoking multiverses we cannot see or consciousness collapsing mechanisms we cannot specify. Does that make it true? No. But it makes it worth considering, worth investigating, worth holding as a live possibility rather than dismissing as science fiction. And there is something else, something harder to articulate. The simulation hypothesis changes how you relate to reality. If the world is rendered, then what matters is experience, not objects. Consciousness becomes central. The inner life becomes the real life. Materialism, the view that only matter is real, inverts. Maybe only consciousness is real, and matter is the illusion, the rendering, the interface through which consciousness experiences itself. This is not new. Mystics have said this for millennia. Buddhists call the material world Maya, illusion. Vedanta says only Brahman, pure consciousness, is real. Plato said the physical world is shadow, and true reality is the realm of forms. The simulation hypothesis is these ancient ideas translated into modern language, expressed in terms of code rather than spirit. Maybe the simulation is not being run by posthuman descendants. Maybe it is being run by consciousness itself, experiencing reality by dividing itself into subjects and objects, observers and observed, creating the appearance of separation to enable experience. Maybe you are not in a simulation. Maybe you are the simulation, consciousness dreaming itself into existence, playing all the roles, forgetting its unity to make the game interesting. This is speculation. This is philosophy. But so is materialism. The belief that matter is fundamental, that consciousness is an accident, that the universe is indifferent to observers, these are also metaphysical assumptions, not proven facts. They feel true because we are used to them, but nothing in physics requires them. Quantum mechanics, if anything, suggests the opposite. So where does this leave us? With uncertainty, with questions, with a universe stranger than we assumed, more dreamlike, more responsive to observation, more entangled with consciousness. Whether it is simulation or something else, it is not the clockwork mechanism Newton described. It is weirder, more participatory, more alive. The question is not whether we live in a simulation. The question is what changes if we do, and the answer is maybe nothing practically, but everything philosophically. It means you are not an accident. Consciousness is not a fluke. The universe is not indifferent. Reality is not fixed. It is rendered, moment by moment, in response to observation. And you are the observer. You are the point. The simulation exists because you are experiencing it. That might be true even if there is no simulation. Maybe consciousness creates reality in base physics too. Maybe the distinction between simulation and reality is meaningless because all reality is observer-dependent at the deepest level. Maybe the universe is not a thing. Maybe it is an experience, and you are having it. Right now, this moment, this thought, this breath, real or rendered, it is yours, and it is all there is.